Now for some real science. The science of Santa. Is Santa compatible with the laws of physics? Or to put it another way, how many laws of physics does Santa actually break? So, for those not familiar with this gentleman, Santa is allegedly a portly, jolly fellow with a white beard and a penchant for wearing red suits. Now, although that must indicate a certain questionable fashion sense, that doesn't mean he can't exist. So what about the claims that are made regarding Santa? Santa, allegedly, visits all households on Christmas Eve to deliver presents to all qualifying children. And by qualifying, of course, he has the naughty, nice list. Can we reconcile this incredible set of feats attributed to Santa with our understanding of science? And my take on this is, can I use any of the science described in my other talks to help us understand whether or not Santa could indeed do what he's claimed to be able to do? So I've got loads of talks, some of which I've not obviously given these talks to you. They're all available if you want to go and watch them online, but I'm going to refer to them occasionally in trying to answer the question about the alleged feats. So this is the sentence we're going to be unpicking. Santa visits households on Christmas Eve to deliver presents to children. So let's unpick that one bit at a time. First, let's deal with children. How many children is he delivering presents to? So the Earth's population is 8 billion or so. It very recently went over the 7.99999 billion and we've clicked over to 8. Approximately 1/4 are children. 50% are eligible for Christmas presents, assuming that Santa is very generous and is not assuming that the children have to be practicing Christians in order to get Christmas presents. So that means about 1 billion children get Christmas presents. And again, we're making the assumption that on his list, there's no naughty children. They're all 100% nice. Any of you who are parents might question that, but let's just assume that everybody is on the nice list rather than the naughty list. So 1 billion children, and Santa visits lots of households. How does he get around? Transport. Okay, first question, can reindeer fly? Well, we know that insects fly. We know that birds fly. We know that pterosaurs fly, though you don't see them much these days. And we know that even some mammals fly. If reindeers can fly, then they choose not to do so for a lot of the time because there's no documentary evidence showing them in flight. But even though there's very little evidence for flying reindeer, we have to remember that absence of evidence is not the same as evidence of absence. So the jury is still out. We cannot prove or disprove the idea that reindeer can fly. Okay. How fast would Santa have to go with his reindeer pulling his sleigh? Well, to visit 1 billion children in one night, by using time zones, that gives him about 36 hours in total, Santa would have to travel at least something of order 2,000 kilometers per second in order to give him a fraction of a second at each household. But 2,000 kilometers a second sounds a lot, but it's only 0.007 of the speed of light. If he's moving at less than 1% of the speed of light, he's nowhere close to defying the laws of physics. We know that no object can travel through space faster than the speed of light, which was measured in one of my talks called Fiat Lux. Now, that's not the same as the expansion of the universe. Remember that galaxies can fly apart from each other at speeds that are greater than the speed of light. We're talking about objects moving through space. They are limited by the speed of light. The expansion of the universe can basically expand at any speed it wants to. So if he does move really fast, wouldn't the sleigh burn up? Wouldn't the reindeer burn up? Aren't we going to look at roast reindeer? If you think of a meteor or an asteroid coming into the Earth's atmosphere, the air in front of the sleigh would be compressed and heat up. Some people talk about friction, but strictly it's not friction that makes meteors or asteroids glow. It's the compression of the air in front of the object that makes them heat up. When I talk about the ABC of stellar evolution, the C of the ABC stands for compression, because when you compress the gas in a star, it heats up and undergoes thermonuclear fusion. And if the air in front of the sleigh heats up, then presumably the sleigh would get hot and start to glow. Even if it was aerodynamic and we take into account the airflow over the sleigh, it would still get warm, surely. Wouldn't the heat make the sleigh glow white hot? If things get hot enough, they will glow. Compression produces heat, hot objects radiate light, and so doesn't that mean that Santa and his sleigh ought to be easily visible in the night sky? Well, maybe it was. But the idea of Santa's sleigh being responsible for a 2,000-year-old idea of the Star of Bethlehem, that's a little bit of a stretch. But maybe Santa's sleigh is visible, and that's the origin of the idea of UFOs. But there is something else that we could consider. There is a type of material that does not emit or absorb or reflect light. In fact, it doesn't interact with any type of electromagnetic radiation at all. That's dark matter. So maybe Santa and his sleigh are made of dark matter, and then that would explain why, even though he's moving around quite fast, there would be no compression that would heat up the sleigh and we wouldn't have roast reindeer. So maybe that's the explanation. Dark matter is the answer. That would also explain why he doesn't show up on radar as well, because again, radar would not be bounced off dark matter sleigh. It would just go straight through, because dark matter does not emit, absorb, or reflect electromagnetic radiation of any kind. So there's one possible explanation. Let's have a look at households. Santa visits lots of households, and he goes down the chimney, allegedly. How could Santa get down a chimney? If he wanted to visit 1 billion children, if we assume that they're all in different families, he would have to squeeze down something like 3,000 chimneys each second. And Santa is a rather rotund individual, a little on the portly side, and so it wouldn't be possible for him to go down 3,000 chimneys each second. However, if you think about what atoms are made of a nucleus and orbiting electrons. If we were to replace the electrons with the heavier muons, which are an elementary particle which are a bit like a heavy electron, then the atoms would be some 200 times smaller. And so Santa would be 200 times smaller if he could somehow replace all of his electrons with muons. So instead of being about 2 meters tall, he would be about 1 centimeter tall, and he would fit down a chimney no problem whatsoever. How he replaces electrons with muons, I don't know, but if he did, then it would not be a problem. But of course that doesn't help if you don't have a chimney in the first place. If you have a house or an apartment that doesn't have a chimney, how is Santa going to get inside? Well, quantum mechanics comes to the rescue. An object can tunnel. In other words, an object can go through what appears to be a solid barrier and come out the other side. So Santa could be outside a house or an apartment in 1 fraction of a second, and he could appear on the other side of a door or a window without ever having gone through the door or through the window. It's a quantum mechanical event, quantum mechanical process, a quantum mechanical event, and if it can happen to a subatomic particle, why can't it happen to a collection of particles such as a Santa? So, no reason why he couldn't appear on the inside of a house, not having travelled through the door or through the window or through the chimney. So what else have we got? Santa visits households on Christmas Eve. So he allegedly does all of this all in one night. How can Santa make so many deliveries all in one night? Even if travelling at relativistic speeds between each delivery, then how can he get everything done in 36 hours? Well, we know from our understanding of quantum mechanics that subatomic particles can be in 2 places at one time. So why can't Santa? It's a very unusual aspect of quantum mechanics, which is why I call the talk on quantum mechanics the weird world of the very, very small. Because, for instance, when we look at subatomic particles, we can think of a little electron spinning clockwise, and simultaneously also spinning anti-clockwise. Now, if we imagine the Earth doing that, it seems to make no sense at all. But it's allowed according to the rules of quantum mechanics, which dictate how the universe is put together. So maybe Santa can be in more places than just one or two. Maybe he can be in thousands of places at once, not disallowed by the laws of physics. If, for some reason, Santa could only be in one place at one time, if you don't like that previous argument, then there are alternative ways he could make deliveries to lots of different points in space. And that is, if he was capable of manipulating space and time, then he might be able to make these deliveries. And we know that every massive object, we tend to think of massive objects being planets and stars and maybe black holes. We know that they distort space and time, but why can't Santa? If massive objects can distort space and time, then maybe Santa has found a way of doing that as well. Right, so Santa visits households on Christmas Eve to deliver presents. He's got to do all of this and take a load of presents with him as well. So how could Santa carry all the presents for these billion children? One present for each child, that means 1 billion presents. How could the sleigh hold that many presents? Well, one option is that the sleigh is bigger on the inside than it is on the outside. Fans of Doctor Who will be familiar with this idea, but actually we know this happens. A black hole, for instance, is bigger on the inside than it is on the outside. So if it's possible for a black hole to distort space and time to allow that to happen, why is it impossible that Santa has figured out how to get the sleigh to do the same thing? And if you don't like that idea, there's another alternative that's allowed by the laws of physics. Why not just store all the presents in another dimension? How do we know how many dimensions there are? Well, we're only aware of 3 spatial dimensions: forward, backward, left, right, up, down. So we know there are at least 3 spatial dimensions. There might be more. Some theorists claim that there must be at least 10 or 11 or 12. So we know there are 3. Maybe Santa has figured out a way of accessing the other spatial dimensions. Maybe there's lots of them. So all he would need to do is to take all his presents, move them into another dimension, and then when he visits each of the places where he needs to deliver the presents, he simply pulls them out from the other dimension back into our dimensions and puts them at the base of the tree. Easy. Yes, you might say. Maybe he can do all of these things, but wouldn't that need a huge amount of energy? If we're talking about Santa and a sleigh and 1 billion presents moving at relativistic speeds, wouldn't that need an absolutely incredible amount of energy? Well, yes, it would. If a black hole can power a starship, why can't a black hole power a sleigh? A small black hole, something no bigger than an atom, would be enough to provide all the energy that the sleigh needs to go at relativistic speeds, in much the same way that we could use it for a starship to actually travel very quickly to nearby stars. But there's another alternative. We don't have to use that. There's an energy source that we're overlooking. What is the elephant in the room as far as the energy that Santa has available to him? What happens to all the mince pies? What if Santa could convert the mass of all the mince pies that he's given into energy through E = mc²? I mean, it's crazy to think that all of the millions of mince pies that are left out for Santa, it's crazy to think that he actually eats them all. So what actually happens to the mince pies, and what if he could convert the mass into energy? Let's do a little calculation and work out how much energy he would be able to access. 1 mince pie is about 50 grams. So the energy equivalent of 1 mince pie is 50 grams times the speed of light squared. That comes out to be about 5 times 10 to the 15 joules per mince pie. We'll come to what a joule is in just a moment. If we assume that a few % of households leave a mince pie and 98% of them don't or something, then let's say, for the sake of round numbers, let's say that 20 million households leave a mince pie for Santa. That's 20 million times the number we just calculated. That's 10 to the power 23 joules that would be available to Santa during the night. Now, it's difficult to work out what that means. If you're a physicist, you're happy to work in large numbers of joules, but for most people, that's completely incongruous as far as a number. So let me put that into some sort of context. If we imagine the energy output of a nuclear power station running for 1 million years, that's the amount of energy we're talking about. If we have a gigawatt power station, multiply that by 1 million years of operation, the total energy that that power station puts out is about 10 to the 23 joules. Santa, in principle, can access that energy in one night. It is an absolutely huge amount of energy. But then you can ask the question, okay, how are you going to extract E equals mc squared from a mince pie? Well, you have a couple of options. One is you take a mince pie and you take an anti-mince pie and you collide them together in the Large Mince Pie Collider at CERN. But then, of course, that begs the question, okay, that gives you a huge amount of energy, but where do you get the anti-mince pies from? So yes, that is a little bit of an issue. But there is another way of extracting not all, but a fairly large fraction of E equals mc squared from a mince pie. We know it's possible because we've seen it happen. If you drop matter into a black hole, you can get an enormous amount of energy out. And we know that happens because matter falling into a supermassive black hole can produce what we call a quasar, which generates an enormous amount of energy. Back in 2020, I took an image of a quasar that is some 25 billion light years away and is producing light, producing radiation because matter is falling into a black hole. And that particular quasar I imaged using a camera without using a telescope. Even at that distance of 25 billion light years, I could image it with my camera simply because there was so much energy pouring out of it because of the matter falling into a black hole. Stars are only about 1% efficient in the sense that when you fuse hydrogen into helium, you only get about 1% of the energy out. In other words, the mass of the star drops by about 1%, and that's your energy. But when you're putting matter into a black hole, it is possible to get not 1%, but 10% or 20% or 30 or 40% of the energy out. You don't necessarily get it all, but you do get a large fraction out. How efficient could it be dropping mince pies into a black hole? Funnily enough, I can't find any data on that. I've tried looking for research papers on how much do you get out of a mince pie falling into a black hole, but very few studies appear to have been carried out. So we know it's possible, we know the answer will be lots, but I don't know exactly how much. But how could Santa do all that? It's all very well saying it's possible, but even if it's possible, how could Santa manipulate space and time in such a way that he would have all the energy he needs to do all of these alleged feats? Well, one thing we do have to bear in mind. Who says Santa has to be human? Maybe Santa has got green skin and big ears. If nobody's seen Santa, how do we know? So, is Santa compatible with the laws of physics? Or to put it the other way, how many laws of physics does Santa actually break? I would argue the answer is none. So feel free to draw your own conclusions about the existence, or otherwise, of the portly, jolly fellow with the white beard and the penchant for wearing red suits. And of course, regardless of your conclusion, the answer is always the same, as I've just done earlier. I'd like to wish you all a very Merry Christmas. Thank you for listening.